Hey there, focus learners. As your caring chemistry teacher, I am absolutely thrilled to welcome you to today's explainer, proudly brought to you by QandA over at QandAHelp.com. So today, we're going to decode a past paper question that, honestly, trips up way too many students on their WAEC, JAM, and NICO exams. But stick with me, because by the time we finish up here, you're going to see exactly how simple and logical this whole thing truly is. Let's dive right in. All right, so here's the challenge we're facing today. It's a classic gas law problem. It asks, when the pressure on 200 cubic centimeters of a gas is doubled and its absolute temperature is halved, its volume would become, and then we get our 4 multiple choice options. Now, this is just a brilliant test of your fundamental principles, because we have to figure out what happens to our volume when both pressure and temperature are changing at the exact same time. I know, it sounds like a lot of moving parts, right? But trust me, we can easily break this down. Okay, the absolute crucial point here is extracting our variables correctly. You see, the best way to beat any complex word problem is to just translate those English words right into mathematical statements. So our initial volume, V1, is 200 cubic centimeters. Easy enough. Then, when the text says the pressure is doubled, well, that just means P2 equals 2 times P1. Next up, the absolute temperature is halved, which simply means multiplying our initial temperature by 1/2, so T2 equals half of T1. And finally, our target unknown is our final volume, V2. Honestly, having this clear little roadmap, that's half the battle won right there. Now, because pressure, volume, and temperature are all interacting simultaneously in our gas container, we can't just rely on Boyle's law or Charles's law on their own. Nope, we need a formula that can handle everything at once. We need our trusty mathematical sword, the combined gas law. So that's P1 times V1 divided by T1 equals P2 times V2 divided by T2. This single, elegant equation just beautifully connects all of our changing variables together. So let's actually get our hands dirty with the math. Our very first job is to isolate what we're actually looking for, which is V2. Rearranging the equation gives us V2 equals P1 times V1 times T2, all divided by P2 times T1. Now we just carefully substitute in those values we extracted earlier. We'll plug in 200 for V1, a half of T1 for T2, and 2 times P1 for P2. And now for the absolute most satisfying part. We can just boldly strike through the identical P1 and T1 terms on both the top and the bottom to simplify everything. That leaves us with a super clean setup. V2 equals 200 times a half divided by 2. Let's finish up that arithmetic, shall we? When you divide 200 by 2, which remember is the exact same thing as multiplying by a half, you get 100. And then when you divide that 100 by 2 again, you arrive perfectly at 50 cubic centimeters. Looking back at the options provided in the exam question, this makes option C our mathematical victor. It really just goes to show how following the mathematical steps makes even the most intimidating questions totally manageable. Actually, wait, let me pause right here for a really vital exam tip. Did you notice that the question specifically uses the phrase absolute temperature? Always remember why the word absolute is so important in chemistry. While gas laws strictly require the use of the Kelvin scale, which starts from absolute zero, we actually don't need to do any tricky Celsius to Kelvin conversions here. Why is that? Because the question gives us a relative change. It simply states the absolute temperature is halved. You can apply that 1/2 fraction directly to your variables without stressing over adding or subtracting 273. Total time saver. And, this brilliantly illustrates what's happening in the real world, way beyond just numbers on a page. I want you to literally imagine a gas-filled balloon in your hands right now. If you physically squeeze that balloon with double the pressure, forcing all those gas particles closer together, it shrinks. Then, if you throw that exact same balloon into a deep freezer, cooling the gas to half its absolute temperature, the gas particles lose energy and slow down, which makes the balloon shrink even more. It's so important to visualize these concepts so you truly, deeply understand the science. So, with that real-world balloon image in your mind, let me reveal a quick visual shortcut for your exams, because you can actually solve this whole thing without the big formula. Just remember the core relationships. Since pressure and volume are inversely proportional, meaning as one goes up, the other goes down, doubling the pressure simply halves our starting volume, from 200 straight to 100. Then, since temperature and volume are directly proportional, meaning they move in the exact same direction, halving the temperature cuts that new 100 volume straight down to 50. 2 quick logical steps in your head, and you get the exact same answer in half the time. How cool is that? Now, using that logical shortcut, we can use the extremely powerful strategy of elimination. We know the final volume absolutely must be smaller than the starting 200 cubic centimeters, because both changes, the squeezing and the cooling, work to shrink the gas. Meaning we can instantly eliminate options A and B, which represent huge increases, and option D, which says the volume stays exactly the same. All of that without even writing down a formula. Option C is literally the only answer that makes logical sense here.
Okay, let's test your newfound mastery with a quick quiz, just to make sure these concepts are really sticking. Imagine a gas has a volume of 300 cubic centimeters. Its pressure is tripled while its absolute temperature remains constant. So find its new volume. I'll pause for just a moment while you apply the logic we just went over.
All right, let's see how you did. Since temperature is constant, we're only looking at pressure and volume, which we know are inversely proportional. If you realize that tripling the pressure means reducing the volume to 1/3, you are absolutely spot on. You simply take 300, multiply it by 1/3, and you successfully found 100 cubic centimeters. Excellent work. Let's try one more quick quiz to truly lock this in for good. A gas has a volume of 200 cubic centimeters. This time, its pressure remains constant while its absolute temperature is doubled. What's its new volume? Think about the direct relationship here. Take a few seconds. Yes, exactly. You've completely got the pattern now, because absolute temperature and volume are directly proportional. When pressure isn't holding things back, whatever happens to the temperature happens to the volume. Therefore, doubling the temperature doubles the volume, taking it straight from 200 up to 400 cubic centimeters. So, to recap our WAEC 2026 journey today, we saw a complex multivariable problem and we broke it down piece by piece. We laid out our original values, recognized that doubling pressure cuts volume in half, and halving temperature cuts it in half again. Whether you choose to use the formal formula substitution method, crossing out the variables, or that logical shortcut method we practiced, both strategies mathematically prove that the final volume of our gas is exactly 50 cubic centimeters, making option C the undeniable winner. I am so proud of your focus today. You've done an incredible job mastering this gas law concept. Keep this momentum going by rushing over to QandAHelp.com for the absolute best preparation for your upcoming exams. You can find tons of resources across all your subjects there. And hey, don't forget to subscribe to our channel for our next explainer. But before you go, I want to leave you with this provocative thought. How many other seemingly complex scientific formulas in your textbooks are actually just simple, real-world behaviors waiting to be unlocked with a visual shortcut? Keep exploring those connections, and I'll see you in the next explainer.